Hey everyone, and welcome back to The Explainer. So today, we are diving into something absolutely crucial. We're looking at one of the most fundamental mechanisms driving modern AI. I mean, how do machine learning models actually extract real meaning from our messy human concepts? We're going to break down the exact mathematical architecture today, step by step, and really explore how a model looks at a string of text, or even an image, and genuinely comprehends it.
To kick things off, let's look at a highly relatable and honestly pretty delicious scenario. Imagine you're building a brand new food recommendation app. A user logs in, and the app goes, "Hey, since you like pancakes, we're going to recommend crepes," right? To us humans, that feels totally intuitive. But think about it. How does the AI actually know that? If you're building this model from scratch, how on earth do you teach a machine that a hot dog is way more similar to a shawarma than, say, a bowl of soup?
Well, to answer that, we really have to look at the tension between two totally different approaches. Back in the day, we used the old method, one-hot encoding. It's this massive, incredibly sparse way to represent data. But the modern solution, and what we're really focusing on today, is embeddings. Embeddings represent data in this dense, elegantly compressed, and frankly, brilliant format.
Let's put this into perspective. Let's say you curate a data set for your new app, and it contains exactly 5,000 popular menu items. Borscht, pizza, salad, hot dogs, the whole shebang. In the old days of one-hot encoding, just to represent a single meal, let's stick with the hot dog, the computer would literally create an input vector that is 5,000 digits long. It's basically a string of 4,999 zeros with a single one stuffed into the exact slot assigned to hot dog. I mean, it is incredibly bulky. Okay, let's dive into this because this sparse data approach, it's basically a catastrophe for your hardware. If your neural network has 5,000 entries and n nodes in its very first layer, it has to calculate just a massive number of weights. This demands an impossible amount of training data, it maxes out your computation, and it just massively consumes your memory hardware. Plus, it makes running models locally on your phone, what we call on-device machine learning, practically impossible. And the worst part of all of this? A 5,000-digit vector tells the machine absolutely zero about what a hot dog actually is, or what it tastes like.
Enter our technological savior, embeddings. An embedding basically maps all that high-dimensional, clunky, sparse data, like our 5,000-digit hot dog vector, into a much smaller, incredibly dense space. And here is the magic of an embedding space. The physical distance between any two points literally represents the relative similarity of those items. So the absolute crucial point to remember here is that proximity equals similarity. Things that are closely related sit right next to each other, and things that are totally different are pushed far, far apart. Let's build a quick visual metaphor to see how this actually plays out. Imagine we take all 5,000 of our foods and we just plot them on a single 1D line. Let's call this dimension sandwichness, okay? So we're measuring from least like a sandwich to most like a sandwich. Where would you plot a hot dog versus a bowl of liquid borscht? Well, the hot dog scores pretty high, so it slides all the way to one side of the line, while the borscht scores very low, moving to the complete opposite end. And this brilliantly illustrates what happens when we give our AI just a little more nuance. If we only had that one single dimension of sandwichness, something like an apple strudel might accidentally fall somewhere between a hot dog and a shawarma, which is just wrong. But the moment we add a second, 2D axis, let's call it dessertness, everything changes. The apple strudel shoots way up on the dessert axis, getting miles away from the savory stuff. Meanwhile, the hot dog and the shawarma, they both score high on sandwichness and really low on dessertness, so they cluster tightly together in this 2D space. Boom! The AI is actually starting to understand their relationship. Now, let's see what happens when we introduce a little depth, a third dimension. We'll call this one liquidness. So now we've got a full 3D culinary coordinate system. Think about the Chinese dessert tung yuan. It's a soup, right? So it's liquid, kind of like borscht, but it's also sweet, so it shares that dessertness with our apple strudel. However, it is definitely not a sandwich. By plotting it across all three of these dimensions, the AI instantly and mathematically comprehends exactly how this dish relates to literally every other item on the menu. Now, 3D is super easy for our human brains to visualize. We get it. But in the real world, AI models are definitely not limited to just 3 dimensions. Real-world embedding spaces often use 256, 512, or even an astonishing 1,024 dimensions. I mean, it's wild.
The model mathematically tunes all these dimensions to capture incredibly complex, hidden relationships in the data. So yeah, those individual dimensions might not translate to simple, fun human concepts like desertness anymore, but the mathematical distances between the concepts remain absolutely precise.
Which brings us to a really massive question. If we aren't sitting there manually plotting sandwichness for every single item, how do the machines actually learn these massive coordinate spaces all on their own? Let's pivot away from our food metaphor for a second and look at large language models. How does a neural network figure out exactly where to place tens of thousands of different words in a vast 1,024-dimensional space? Well, the secret lies entirely in how they're trained. Take a classic model like Word2Vec. It uses this frankly brilliant method involving something called skipgrams. Basically, the AI processes a massive, massive body of text. Think every English novel on Project Gutenberg or literally all of Wikipedia. It takes a target word, looks at the context surrounding it, and tries to predict the nearby words. So, for example, if it reads, "They rode a horse down into the canyon," and then later reads, "They rode a burro down into the canyon," the AI learns that horse and burro appear in almost identical context. It's essentially playing the world's largest game of fill in the blank, millions and millions of times. And the actual architecture making that prediction possible, it's fascinating. Inside the Word2Vec neural network, your one hot encoded word passes right into a projection layer. And crucially here, there are no activation functions in this step. It is purely just learning the weights. Then the data moves through a hidden layer to process and finally pops out at an output layer that uses a softmax function to normalize the predictions. During this whole training process, as the network gets better and better at guessing those nearby words, it constantly tweaks the weights in that projection layer. And here's the kicker. Once training is totally done, if you stack all the learned weights for a single word, that stack literally becomes our dense embedding vector. The weights literally are the coordinates. But look, as incredible as Word2Vec really is, it has a bit of a fatal flaw. It generates what we call static embeddings. That means every single word gets one fixed point in the embedding space, no matter what. Today, though, the absolute cutting edge of AI relies on contextual embeddings. This is where the coordinates of a word dynamically shift and change based on the actual structure of the sentence it's in. To really understand why static embeddings fail, just ask yourself this. Is the word orange a fruit or is it a color? If you're using a static embedding from a standard dataset, orange gets assigned one single coordinate. And because orange is so frequently used as a color in text, it usually gets placed right next to yellow in the embedding space. So its 14th nearest neighbor might be juice, but its absolute closest friends are always going to be colors. It's rigid. So the crucial point here is perfectly illustrated by this one sentence. I drank orange juice while looking at the orange sunset. In an old static model, the AI uses the exact same coordinates for the word orange both times it appears, which severely limits its actual understanding of what's happening. I mean, this single sentence clearly demands two completely different mathematical coordinates for the exact same word, entirely depending on what sits next to it. And that is exactly what contextual models manage to pull off. These modern architectures completely solved the orange problem. Early on, models like ELMO aggregated embeddings by reading sentences chronologically and then in reverse. Then BERT came along and took it even further, masking parts of the sequence to forcefully learn bidirectional context. And today's transformer models, the absolute powerhouses behind modern generative AI, use self-attention layers. They mathematically weigh the relevance of every single other word in the sequence and combine it with a positional embedding matrix. Basically, they mathematically blend a word with its neighbors to create a unique, fully dynamic coordinate for every single context it's ever used in. It is truly breathtaking when you step back and look at the big picture. From realizing that a hot dog and a shawarma share underlying mathematical coordinates, all the way to reading a complex sentence and dynamically mapping the shifting, fluid meanings of words in a 1,000-dimensional space. Embeddings really are this secret bridge between human intuition and machine mathematics. Which leaves us with a pretty profound thought to ponder today. If AI already understands the nuance of our world through these incredibly complex contextual coordinates, what other hidden mathematical dimensions of human thought will it uncover next? Thanks so much for joining me on this explainer. Keep wondering, and I'll catch you next time.